Hey, let's talk about what you need in order to do this. So we're gonna go through some of the questions for this. And so before we start, what you're gonna be doing as you do this after answering these questions is figuring out Lewis structures, figuring out molecular geometry, and then, especially later on, once you figure out your Lewis structures and electron molecular geometry, figuring out whether it has resonance or not, polar versus nonpolar bonds, polar versus nonpolar molecules. So before you get started with this, you need some things. One, in order to figure out the Lewis structures, you need to know valence electrons, so make sure you get a periodic table handy. Make sure you also go to your notebook and find this worksheet, Predicting Chemical Bond Types, because it has this, and you need this in order to do these here on the back side to find out whether the bonds are polar or not. So go get hold of a periodic table, find this worksheet, Predicting Chemical Bond Types, and a calculator might be handy for subtracting out the numbers in order to get the bond types. Okay, so let's adjust the camera a bit. And let's get started going through some key questions here, beginning with, of course, the very first thing of you got to know your shapes in order for this assignment to make sense. So person would need to know that this is trigonal pyramidal, that this is trigonal planar because it's flat, that this is bent, that this is tetrahedral, and that this is linear. Furthermore, it's going to be important for anybody doing this worksheet to understand that if we ask you for the shape of something, it depends. Do we mean the shape, or actually, let me back up a sec. When I say the shape, I mean the geometry of something, okay? So when we say molecular geometry, we mean molecular shape. When we say electron geometry, we mean electron shape. If we're talking about the atoms and not the non-bonding electrons, then you're talking about molecular geometry. And if you're talking about the kind of geometry that involves only the electrons, you don't care about the atoms, you're just looking at the bonding and non-bonding electrons, you're talking electron geometry. So let's begin. Adjust this to get that part out of the way. First, just a quick justification of why these are what they are. So with your 8 valence electrons, you come up with this Lewis structure for methane, same thing for water. Why is the electron geometry tetrahedral? It's because you look at the electrons. See that bond? That's 2 electrons. This bond is also 2 electrons. There are 1, 2, 3, 4 sets of electrons coming off the central atom. Geometry is based around the central atom. So the only possible shape for 4 things around the central atom is tetrahedral. That's why electron geometry is tetrahedral. This also has 1, 2, 3, 4 sets of things off the central atom, and the only possible shape for 4 things off the central atom is tetrahedral. That's why these have the same electron geometry. And why does that have molecular geometry? Because it has 4 atoms off the central atom. 4 atoms are attached to this one in the center. The only possible shape for 4 things attached to it is tetrahedral, which, as a reminder, is this shape, 1, 2, 3, 4. So I suppose another way to justify that is electron geometry. If you have 1, 2, 3, 4 sets of electrons, that's tetrahedral. If you also have 1, 2, 3, 4 atoms, then that's tetrahedral molecular geometry. Here we say bent for molecular geometry because there's only 2 atoms. And it looks linear in here, but it's not linear, it's bent. Why? It's because this represents bonding electrons, which are negatively charged. These are also negatively charged. So the bonding electrons would love to be linear like this, but because there's these non-bonding electrons, they force the non-bonding ones out of the way, and that's what makes it into a bent shape. Here's a model that sort of gets at that idea. This represents this, And those two hydrogens are represented by these white spheres right here. That oxygen is represented by this black sphere. I know technically I should be using red, but whatever, black it is. They would love to be straight across from each other like this linear shape right here, but they can't because the electrons in these bonds get pushed out of the way by the electrons in these, which represents non-bonding pairs right here. So this is tetrahedral electron geometry, because you see there's 4 sets of electrons, but bent molecular geometry because the molecule is composed of these atoms. We just look at these 3 atoms. Oh, that's a bent shape. Okay, so that's the reason for that. Now, why do we say these have no resonance? Because there's no other way to arrange the electrons. This is the only way. If you put the electrons anywhere else, it's wrong. It violates the octet or duet rule. The polar bonds, if you subtract carbon from hydrogen, carbon and hydrogen, there's a difference of 0.4. That makes polar bonds. For oxygen and hydrogen, oxygen's 3.5, hydrogen's 2.1. 3.5 minus 2.1 equals 1.4 difference, which is a polar bond. These both have polar bonds. This is a structure that you look here at the molecular geometry. This is a shape that balances out, and because it balances, those polar bonds balance out to make a nonpolar molecule. As a reminder, there's certain shapes such as tetrahedral, trigonal planar, or linear, where they balance out so that polar bonds can cancel each other out to make a nonpolar molecule. So these can have polar bonds but be nonpolar, even if the individual bonds are polar, simply by virtue of their shape, as long as each of the bonds is the same kind of bond. Whereas other shapes, such as maybe bent or trigonal pyramidal, which are not symmetrical and don't cancel each other out, if these have polar bonds, the molecule remains polar. That's the reason why a tetrahedral geometry with polar bonds produces a nonpolar molecule. They balance out. Whereas a bent molecular geometry with polar bonds fails to cancel, which means it remains polar. So that's the reason for those answers. Now let's make sure this is properly lined up. Okay, so let's go through and do another example. Carbon tetrachloride. 32 valence electrons, conveniently calculated for you. So there's carbon, and I'm going to put the 4 chlorines, Cl, 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 and Cl. And then let's add until I got 32. So that's 2, 4, 6, 8 so far. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 chlorines, or 32 electrons, sorry. Stop, because don't keep going, and then just check. This has 8 electrons, that satisfies the octet rule. This has 8, this has 8, this has 8, and this is 8. Octet rule satisfied. This is total number of electrons correct, octet rule satisfied. If there was hydrogen, I'd also try the duet rule. Basically, it's all good. Electron geometry. I look at the central atom. 1, 2, 3, 4 sets of electrons coming off the central atom. When I say sets, I mean pairs. That's a pair of electrons, 2, 4, 6, 8. Okay, so 4 sets, that means tetrahedral. And then when I look at 4 atoms, that's also tetrahedral. Notice, sometimes the answers are the same, sometimes they're not. What's the difference? Do you notice the central atom has no lone pairs here, and it's the same? The central atom here has no lone pairs, and it's the same? This central atom does have lone pairs, and it's not the same. Whenever you have lone pairs, you're going to get different answers. No lone pairs, same answer. No lone pairs, same answer. All right, next. Does it have resonance? No, there is no other way to arrange these electrons. If you move these, maybe like form a double bond or something like that. I mean, you could, but now that's too many electrons, and if I move that, get rid of that, so I just turned this into a double bond, for example, now I just violated the octet rule. So there's nothing you can do with this to make it have the right number of electrons and rearrange it, which means leave it alone. You can't. There's no resonance. Now it has polar bonds. Look at the molecular geometry though. It's a shape that cancels. It has polar bonds. That makes it non-polar molecule overall. Because, yes, they're polar, but they're polar in opposite directions in a way that cancels out, turning them in polar bonds into a nonpolar molecule overall. Let's do nitrate. So, nitrate, that's NO3. Nitrogen has 5, oxygen has 6. I got that by looking at the periodic table. Nitrogen has 5, oxygen has 6. There's 3 oxygens. And can't forget to add 1 because of the charge. I'll put that right here, 1 plus. And what that adds up to is, well, actually, right here. So I guess I could have done all that math here. 1 plus 5 plus 3 times 6. And that comes to an answer of 18, 23, 24. 24 electrons. So nitrate, put that one in the middle, spread the oxygens around, add until you got 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh, okay, well, that's it. So I have correct number total, and I satisfied the octet rule for oxygen here, satisfied octet rule for this one, satisfied octet rule for this one, but not for this one. So what do? I take one of these and bring it here to make it a multiple bond, and it could have been this one, it could also have been this one, so I didn't really pick this one for any good reason at all, just because. So let's change that back. Let's make that a double bond. And now it's still 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But now oxygen has a satisfied octet rule and nitrogen. Let's give it brackets. Charge. All right. Electron geometry. What's the electron geometry? The electron geometry is 1, 2. Yes, this is only one domain here. So this is one domain, another domain, another domain. I only see 3 domains here. Whenever you have 3 coming off the center of something, that's this shape, trigonal planar. And because there's no lone pair, the 2 are going to have the same answer, because 1, 2, 3 atoms. Trigonal planar. And then there's resonance. Why is there resonance? Because that double bond, yeah, it's here, but it could have been here or it could have been here, and it would be equally legitimate. So for that reason, there's more than one way to put together. It has resonance. Now, the bonds, look, I already did this for you, are polar. But they're arranged in this shape, which balances out. So you have polar bonds in a shape that balances, because remember, you look at the molecular geometry, that makes nonpolar, because they balance. Okay. Let's move this on. All right, let's do this one. Ammonium, number of valence electrons. All right, let's see. Nitrogen has 5, and hydrogen has 4. Whoops, sorry. Hydrogen has 1, and there's 4 of them. And then I'm going to minus 1 because of that plus charge. Gives you a total of 5 plus 4 is 9, minus 1 is 8 electrons, valence electrons. Lewis structure, N. Let's put the 4 hydrogens around. Let's put the brackets in charge. Now let's check 8 electrons. 2, 4, 6, 8. No need to add any, it's good. Electron geometry, I see 1, 2, 3, 4 sets of electrons around. That's tetrahedral. 1, 2, 3, 4 atoms, which means molecular geometry is tetrahedral. I mean, after all, there's no lone pairs, so same answer. Resonance or no resonance? There's no other way to move these electrons. It's just the only way they can be. So that's why I say that. Polar or non-polar bonds show work. All right, this is where you get hold of that one worksheet. Hydrogen and nitrogen. So hydrogen and nitrogen. You can subtract them in any order. You're going to get the same number, but I'll just put the bigger number first. So nitrogen's a 3.0. Subtract the smaller number, 2.1. And that equals 0.9. A difference of 0.9 means polar bonds. But notice, molecular geometry tetrahedral. Remember, tetrahedral is a structure that balances. So polar bonds cancel out to make a non-polar molecule. Now here with the boron tribromide, how many valence electrons does it have? You look at boron, which is 1, 2, 3 valence electrons. And then bromine has 7. So, 3 times 7, which is 21. This is 3 plus 21, which equals 24 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Look at that, pre-done for you, but confirming that it's right. What geometry? Electron geometry, 1, 2, 3 things off the center atom. Trigonal, planar is the only possible thing to have when you have 3. No lone pairs, so same answer for molecular geometry. No resonance because there's no other way to arrange these electrons without messing something up. Boron doesn't follow the octet rule, so just leave it as is. I mean, I know you could move one of these to be like a double bond and make boron follow the octet rule, but it just doesn't. Leave it alone. All right, nonpolar bonds, which means nonpolar molecule. Now, it's not, the reason this is a nonpolar molecule isn't because the shape, although trigonal planar can have polar bonds cancel to make a nonpolar molecule. The reason we put nonpolar here is because the bonds are nonpolar. So it doesn't matter what shape you have. If the bonds are nonpolar, your molecule is nonpolar and that's it. So the only way you ever put polar here is if you have polar bonds and then some shape that doesn't balance. So let me see something for a moment. Okay, so these are going to follow the same general ideas as up there. So the same methods I employed here, you employ down here. So I'm going to leave that for the viewer to complete on their own. Let's talk about some of these more complex ones. Ethene, C2H4. All right, let's total up the valence electrons for that one. The valence electrons, carbon has 4, and there's 2 of them. And then hydrogen has 1, and there's 4 of them. That means 8 plus 4 equals 12. So, all right, so 12 electrons. Let's put this together. The first thing we do is put our 2 carbons there first, so they'll be our ones in the middle. We'll put our 4 hydrogens spread evenly around. 1, 2, 3, 4. All right, that's step 1. Well, step 2, step 1, count your valence electrons. Step 2, build a molecule. Step 3, let's spread around those electrons. 12, 2, 4, 6, 8, 10. 12? I don't know, I guess somewhere. Got to put them somewhere. I'm not putting that on the hydrogen because hydrogen's duet rule. You can't have more than one bond. No lone pairs. All right, well, that leaves this carbon is okay. It's got 8 electrons, but this one violates the octet rule. Not to mention carbon does not like having lone pairs. So I'm going to take that lone pair and move it here to be a double bond. That way there's no lone pairs. And now this carbon has 8 electrons, and this carbon also satisfies the octet rule with 8 electrons. All right, that said, technically I now have 2 central atoms. Both these carbons are a central atom, though because they're both attached to 2 hydrogens and double bonded to a carbon, they're going to get the same answer, so I only need to write one answer. So for ethene, I am going to put that this is, let's see, this is electron geometry right here. I look at each central carbon. It has 1, 2, 3 sets of electrons on it. This is one part of electrons, one bit of electrons, one here. So 1, 2, 3 electron domains means trigonal planar. It has 3 atoms attached to it, which means trigonal planar. And after all, there's no lone pairs, so same answer anyway. Now, does it have resonance? And the answer is no, because if you move these electrons around, you're going to violate the octet or duet rule. There's nothing you can do. No resonance. Now, you have 2 kinds of bonds around the carbon, which means we need to do 2 calculations here. What kind of bonds are involved? So we have carbon-hydrogen and carbon-carbon. Now, carbon-carbon bond, that's a very easy calculation. That's the bond right here between the carbons. That's 2.5 minus 2.5 equals 0, nonpolar. Carbon-hydrogen, on the other hand, hydrogen's 2.1, carbon's 2.5, so 2.5 minus 2.1 equals 0.4. That's a polar bond. Well, polar covalent, but we'll just say polar for shortness' sake. Okay, we've got 2 different kinds of bonds. So here's the thing. We have trigonal planar. Trigonal planar is a shape that cancels. But it's a shape that would cancel if all 3 bonds were the same kind of bond. They're not. We have a polar bond for one of them, and then for 2 of them, and then a nonpolar bond for one of them. For that reason, not all bonds are the same. So even though it's a shape that cancels, because it's not all the same bond, they fail to cancel out. I'm going to say polar molecule. At least based on what we're talking about in this class. Now, in the bigger picture of things, I would say that these ones work in the opposite direction. They cancel each other out. But based on what we've told you guys in this class, we're going to go with polar molecule for the answer, because when you look at just a central atom, you have bonds that are not all the same, and some are polar and some are not. And so that makes failure to cancel, aka polar molecule. Next, here. Okay, let's do this real quick, and then we need to talk about these. So, methanol. It is all that. How many electrons is in there? So, 1 carbon, that's 4. 4 hydrogens, don't forget that's 1 hydrogen plus 1 more. So that's 4 times 1 plus oxygen is 6, which means 4 plus 4 plus 6, which equals 14. 2, 4, 6, 8, 10, 12, 14. Okay, good, confirmed, all set. Now, we've got an issue. This is a central atom, and so is this one. You have 2 central atoms, and they're not the same as each other. These 2 central atoms are the same, so one answer sufficed. Because these are not the central atoms, you have 2 different answers. Around the oxygen, you have one answer, and around the carbon, you have another answer. Though that said, for electron geometry, both of them have 4 domains. See, there's 4 sets of electrons around the carbon, 4 pairs of electrons around the oxygen. They both have tetrahedral. For molecular geometry, oxygen and carbon, for molecular geometry, this has lone pairs, this doesn't. You have different answers. Oxygen, 2 lone pairs and 2 atoms. Remember, those atoms look linear here, but they get bent and forced out of the way by the repulsion of these lone pairs, which means bent molecular geometry. Whereas around the carbon, there are 4 atoms, which means, and no lone pairs, which means tetrahedral. There's no way to move these electrons, so you got no resonance for both of them. Now, bond polarity. Oh, we've got a few here. All right, we have carbon hydrogen. We have carbon oxygen. We have oxygen hydrogen. So for carbon hydrogen, that's 2.5 minus 2.1. (2.5 minus 2.1 equals 0.4, which is polar. Carbon oxygen is 3.5 minus 2.5. 3.5 minus 2.5 equals 1.0, which is polar. Oxygen hydrogen, 3.5 minus 2.1. 3.5 minus 2.1 equals 1.4, which is polar. So we got all polar bonds. Polar, polar, polar. But they're different kinds of polar. So around the oxygen and around the carbon, we're going to give answers. Though I think it's going to turn out to be the same answer, but nonetheless, let's justify why. Bent molecular geometry, this shape fails to cancel anyway. So because we have polar bonds, all of them are polar, and you have bent, which is a shape that doesn't cancel anyway, it's a polar molecule. And then tetrahedral, around this, tetrahedral is a shape that cancels. However, they're not the same bond. Carbon, hydrogen, carbon, oxygen, they're not four of the same bond. Because of that, cancellation does not happen. It remains a polar molecule. And to be fair, these are part of the same molecule. So if any part of it is polar, the whole thing is polar. So technically, you could just write polar molecule once for the whole thing. All right, but that's how that goes. Now, onward. Let's do carbon dioxide. So for CO2, that's carbon has 4 valence electrons. Oxygen has 6, and there's 2 of them. 16 valence electrons. Oxygen, carbon, oxygen. Put carbon in the middle. 2, 4, 6, 8, 10, 12, 14, 16, done. Octet satisfied, octet not satisfied. So let's take one of these pairs of non-bonding electrons. For no good reason, I'll pick this one. Maybe just because it looks pretty. And I'll put it here. And I'll take this one and put it here. And that gives octet. So it gives octet and an octet here and an octet here. So that's good. We've satisfied it. We've got the correct Lewis structure. So next, there's only one central atom, so we only need one answer for each of these. I see a carbon for the electron geometry with 2 sets of electrons on either side. I'm aware it's a double bond, but you treat it as one domain. So it's only got 2 domains and no lone pairs. So that means with 2 domains, you get linear. And then as far as there's no lone pairs on it, which means same answer here, because there's 2 atoms. And with nothing to push them out of the way, they'll just be straight across from each other, linear. All right, does it have resonance? Actually, yes, it does. Why does it have resonance? Because you could turn this into a lone pair and turn this into a triple bond. Watch. Carbon, triple bond with an oxygen. See, I just turned one of these into a triple bond. I'm going to put this back into a lone pair. Single, and then. So this is an alternative way, and it satisfies the octet for here, and here, and here. This is a lot less stable than this form, but it could theoretically happen. It is valid, so we'll say since there's more than one way to arrange the electrons, yes, it has resonance. Now, we only have carbon-oxygen bonds here. So I'm going to look up carbon and oxygen, which is 3.5 and 2.5. So 3.5 minus 2.5 equals 1.0, which is polar bonds. But since it's linear, that means polarity going in opposite directions. So what that means is they cancel out to make non-polar molecule. All right, now for this next one down here, you've got basically the same considerations as before. Complement of electrons. It's got a lone pair, so you'll have different answers for these. I can see resonance here because this double bond could have been here, so it will have resonance. And then for the bonds, just as a heads up, it's oxygen minus itself. 3.5 minus 3.5 equals 0, nonpolar, which means it actually doesn't matter what the shape is. Nonpolar bonds mean nonpolar molecule, and that's it. That's all there is to it. All right, the last one, phosphate. Look, it violates the octet rule. Yes, there's many that do that in real life. That's why you were given this pre-drawn molecule. So let's see, phosphate, PO4 with a 3 minus charge. That's phosphorus is 5 valence electrons, 4 oxygens with 6 valence electrons each, plus 3 in order to reflect the 3 minus charge means 5 plus 24 plus 3, which equals 32 valence electrons. And then you count out 32. Now, next thing, the fact that you have a double bond here and 3 single bonds doesn't change the fact that it's 4 domains surrounding the phosphorus, which means tetrahedral. It also doesn't change the fact that there's no lone pairs around the phosphorus. Same answer. And you can think of it also as 4 atoms. Well, what's the shape of 4 atoms clinging to the central atom? It's tetrahedral. Does it have resonance? Sure, because that double bond could have been here or here or here. Resonance. Now, what about the polarity of the bonds? Let's look that up. Phosphorus is 2.1, oxygen is 3.5. Difference of 1.4, that's polar. Now you have polar tetrahedral structure. That means it balances out. Polar bonds cancel, become a nonpolar molecule. All right, that's how it goes. Happy stuff.